Principle of superposition. Principle of superposition with respect to electric field. If there are number of charges like this, Q2, Q3, Q4 and this Q1, then what is the resultant force on Q1 due to these charges? Means it is the vector sum of the force due to two charges taken at a time. So F equal to F1 2 plus F1 3 plus F1 4. This is just a notation. This represents force on Q1 due to Q2, force on Q1 due to Q3. Suppose Q2 is positive and Q1 is also positive, then there is repulsion between these two. Repulsion means like this. You have to concentrate on Q1. Repulsion means like this. So force on Q1 due to Q2 is this along the line joining the charges. That we know. Now if Q3 is also positive, then there is repulsion between Q1 Q3 like this. Then force on Q1 is away along the line joining the charges. Suppose Q4 is negative, then there is attraction between these two. Attraction means like this. Again, concentrate only on Q1, the direction in which Q1 moves. Therefore, this is force on Q1 due to Q4. This is F1 3. This is F1 4. Now we have to find the resultant of these three vectors. Resultant of these three gives the resultant force on Q1 due to other three charges. So that's how we can use principle of superposition. Force on any charge due to a number of other charges is the vector sum of all the forces on that charge force on any charge due to number of other charges is the vector sum of all the on that charge due to the other charges taken one at a time. The individual forces are unaffected by the presence of other charges. So this is principle of superposition. Consider a system of charges Q1, Q2, Q3, etc. Qn. Force on Q1 due to other charges is force on Q1 equal to force on Q1 due to Q2 plus force on Q1 due to Q3 plus etc. plus force on Q1 due to nth charge. Force on Q1 is F1 equal to, constant is common factor, that constant is 1 by 4 pi epsilon naught. Remaining is Q1 Q2, force between Q1 Q2 by R12 square into, since it is a vector, there should be a unit vector which gives direction, R12 cap plus force between Q1 and Q3 So it is R13 square. So it is R13 cap plus Q1 Qn. What is this? It is force between Q1 and Qn, last charge, by R1n square into R1n cap. So in general, nth term is 1 by 4 pi epsilon naught. Sum of these terms means, let us write summation of Q1 Q2 Q1 Q3 Q1 Qn. Q1 is there in all the terms, Q1. The other is Qi by R1i square, Q1 Q2 by R square, Coulomb's law, into R1i cap, where I is from 1 to n. Electric field at a point is the electrostatic force on a unit positive charge at that point. So unit positive charge is the test charge. Okay. So electric field is equal to limit of force by charge as Q naught tends to 0. Again, limit Q naught tends to 0 means the magnitude of test charge should be very small, as small as possible. Where F is force, Q naught is test charge, meaning of limit Q naught tends to 0, test charge should be very small and its presence should not alter the field. SI unit of electric field is Newton charge. It is Newton per Coulomb. There is one more unit, volt per meter. Okay, we will see this later. Time being, electric field is Newton per Coulomb. Electric field is a vector quantity. Dimensional formula is this is Newton. Newton is ml t minus 2. Q naught charge. We know that charge should be expressed in terms of ampere time. Simplify this. It is m L, this t goes to numerator, becomes t minus 3, a minus 1. ml t minus 3, a minus 1. Expression for electric field due to a point charge. Electric field at a point is the force per unit charge, force per unit positive charge placed at that point. Consider a point charge Q placed in air at O. Why we consider air or vacuum? Just to make epsilon r equal to 1. Okay. Let P be a point at a distance R. Let P be a point at a distance R from Q0. Let P be a point at a distance R from Q0 where a test charge is placed. Let this be Q plus Q. This is point P. And at point P, we should keep Q0. Charge Q0. This is the test charge. Distance of P from Q is R. This is positive charge. Test positive charge. This is given charge. This is also plus. Because of repulsion, the Q0 moves away like this. Of course, Q also moves away, but concentrate on Q0. So direction of force on Q0 is away. So this is the direction of force. F. If this is the direction of force, then this is the direction of electric field. Let us write force between Q and Q0 according to Coulomb's law. According to Coulomb's law, force on Q0 is F equal to constant Q0 by R square, distance square, and this constant is 1 by 4 pi epsilon naught into Q0 by R square. Here epsilon naught is absolute permittivity of free space. But electric field E equal to limit of force by charge as Q0 tends to 0. Therefore, electric field equal to limit of Q0 tends to 0. Force is here 1 by 4 pi epsilon naught Q0 by R into 1 by Q0. 1 by Q0. Observe, Q0 get cancels. If there is no Q0 term, then limit Q0 tends to 0 is meaningless. So we can drop this. Therefore, electric field equal to 1 by 4 pi epsilon naught Q by, this is square, Q by R square. In vector form, electric field equal to 1 by 4 pi epsilon naught Q by R square into R cap. Constant Q by R square. Force is constant Q1 Q2 by R square. If Q is greater than 0, means for positive charge, electric field is away from Q. These directions are important. If this is Q, given charge, this is point P. So electric field at point P is away from the charge if this charge is greater than 0 for positive charge. What is the physical significance of this direction means? If we keep a positive charge here, test positive charge, the test positive charge moves in this direction because of this positive charge. That is the meaning of the direction of electric field. If Q is less than 0, means for a negative charge, electric field is towards Q. This is Q, given charge. This is point P. If we keep a positive test charge, and this is negative. If this is negative, this is positive test charge, then this positive test charge is attracted towards the given charge. So this is the direction of force, means this is the direction of electric field. Observe, because of positive charge, electric field is away. Because of negative charge, electric field is towards at this point. So we should draw the vector from that point. We should draw the vector from that point. Okay. Force on a charge Q in electric field E. If there is some electric field, in that electric field, if we keep Q, then this experiences force. And what is the force means? Force equal to Q times electric field. So direction of electric field is the direction of force, or direction of force is the direction of electric field. Here we understood that the direction of force is the direction of electric field. Here we can say the direction of electric field gives the direction of force for a positive charge. If this is uniform electric field E, and if we keep positive charge, this positive charge experiences force in the direction of the field. If this is a negative charge like electron, then this charge experiences force opposite to the direction of electric field. So that is the meaning of F equal to Q into E. Relation between electric force, electrostatic force and electric field. Electric field lines. These electric field lines are imaginary lines which represents electric field. And what is the basis of writing imaginary lines means? The direction of motion of test positive charge is the reference. For example, if this is the given charge, keep a test charge here. This test charge is positive and very small. There is repulsion between these two charges. As a result, this test charge moves in this direction. So in the direction of motion, draw one line. Now keep the test charge here. This test charge is repelled by this parent charge. So this is the direction of electric field. Direction of force is the reference for electric field line. Keep test charge here. This moves away because of repulsion. Because of repulsion. Because of repulsion. Because of repulsion. So we can draw lines like this which represent electric field lines. Suppose for a negative charge, given charge is negative, but test charge is always positive because this is the reference. By convention, this is taken as positive. By convention, test charge is always positive. Okay. So this charge attracts this positive charge, test charge. Therefore, this moves in this direction means in the direction of force, draw a line. This is the direction, this is the electric field due to negative charge. Now keep test charge here. Again, this is attracted towards minus. Observe the direction of electric field lines. Positive charge is attracted towards this negative. So electric field lines are radially inward. Positive charges are taken. Positive charge, positive charge. So from this we should draw electric field line. From this also electric field line. From positive electric field line. This also from positive charge. And the direction, you know, for a positive charge electric field is always outward. So concentrate on the direction. These are the electric field lines due to identical point charges, identical positive point charges. If the identical charges are negative, okay, for negative and negative also we should draw the same pattern. But direction should be opposite. Towards negative charge. Like this. Only directions are different. Now what if positive and negative charges are taken? Plus and minus. Electric field lines are away from positive and towards the negative. Therefore, we should draw lines like this. Positive to negative. Positive to negative. Positive to negative. Okay. Again, same question. What is the meaning of the direction? Means the direction of electric field lines gives the direction of motion of test positive charge. Now for this line, if I keep a test charge here, positive charge, this test charge is repelled by plus in this direction. At the same time, this positive charge is attracted by negative in this direction. These two are vectors. Therefore, resultant of these two will be along the tangent. See, if you draw tangent for an electric field, that tangent represents the direction of motion of test positive charge. So field lines, direction of field lines are important. An electric field line in an electric field is an imaginary straight or curved path along which a test positive charge moves or tend to move. Now, let us go through the properties of electric field lines. Students, you have to copy all these properties. Properties of electric lines of force. Electric field lines start from positive charge and ends at negative charge. This you know. Plus charge means electric field lines are away, and for negative charge electric field lines are towards. And what is the reference for this direction? The direction of motion of test positive charge. In a charge free region, electric field lines can be taken to be continuous curves without any breaks. Charge free means there should not be any other stray electric charge. In that region, it is continuous without any breaks. We have seen in the case of plus and minus. Here, because of positive charge, continuous. Because of negative charge, continuous. Isolated positive, isolated negative. Okay, isolated means positive charge alone, negative charge alone. That is the meaning charge free region. If there are two charges, then in a system of two charges, lines are also continuous. See, there is no break in this electric field line. Two lines of force never cross each other. If they do so, then at the point of intersection there cannot be unique direction for electric field line. Therefore, the lines cannot intersect. So this is a important property. If this is one electric field line, this is another electric field line. So in my case, they intersect. What is the direction of electric field line means? The direction of motion of test positive charge. Now, if I keep test positive charge here, this moves along the tangent drawn at that point. At this point, if I keep test positive charge, it moves in the direction of the tangent. If I keep at this point, it moves in this direction. At this point, it moves in this direction. But if I keep the test positive charge at the intersection, then there is ambiguity. In which direction the point charge has to move? Is it in this direction or in this direction? Since this test charge cannot have two different directions at the same time, this type we should not draw. Please understand, we should not draw electric field lines which are intersecting. It could be something like this. And we should not show this intersection. Electrostatic field lines do not form closed loops. Of course, for isolated charges, point charges. Because for point positive charge radially outward, point negative charge radially inward, if there are other charges, then it forms closed loop. Otherwise, no. The electric field lines possess longitudinal tension, which illustrates attraction between opposite charges. Let me consider plus and minus opposite charges. Field lines are from positive to negative. We know this. From positive to negative. If you observe the electric field lines, this resembles a stretched rubber band. Stretched rubber band means that has the tendency to contract lengthwise. Because of attraction, there is contraction. So this pattern also similar to that. Therefore, we can imagine that there is longitudinal tension in these electric field lines, which illustrates attraction between the charges. The electric field lines exert lateral pressure, which illustrates repulsion between like charges. Now, consider like charges plus and plus. These are the field lines due to plus and plus. It appears these electric field lines are exerting pressure on the neighboring. These exerting pressure on neighboring. So, we can imagine that there is repulsion between these two charges because of lateral pressure of these field lines with this set. It is merely imagination. Okay? The field lines are always perpendicular to the surface of a charge conductor. This is one of the properties of electric field lines. We are going to prove this. For time being, if this is a conductor, charged conductor, then electric field line is always perpendicular to the conductor. For a sphere, perpendicular means the line should be along the radius. So this is the electric field line drawn at this point. Let me draw perpendicular at this point. Tangent to the tangent perpendicular. This is the electric field line. If this is a sheet of charge, plus sheet of charge, then electric field lines due to this sheet of charge is again perpendicular to the conductor like this. That is the meaning of the field lines are always perpendicular to the surface of a charged conductor. The electric field lines do not pass through a conductor. True. They won't pass through a conductor. We are going to prove this also. The electric field lines are crowded in a region where field is strong and spread out where the field is weak. Observe these two cases. In this region, electric field lines are crowded. Means electric field is strong, closer to positive charge. Here, less crowded. Less crowded means, spread out means weak field. Similarly, stronger field, weaker field. Suppose field lines are like this. In this region, electric fields are crowded. Electric field lines are crowded means this represents stronger field. Less crowded means weaker field. That is this. Electric field lines are crowded in a region where field is strong and spread out where the field is weak. This is how we should draw. Please understand, this is how we should draw. These are imaginary lines. Okay. Now assignment questions, question bank, anything. What is electric field? 1 mark question. Define electric field strength at a point. What is electric field means? These are imaginary. What is electric field means? These are the electric field is the region around a charge where another test charge experiences force. Define means try to use electric field equal to force by charge. So this is taken as the definition. Electric field is force per unit positive charge placed at that point. Mention SI unit of electric field. Newton per coulomb. You can also write volt per meter. In second chapter we will see how it is volt per meter. 1 mark, 1 mark. What is the physical significance of the direction of electric field? Physical significance of direction means the direction of motion of test positive charge is the direction of electric field line. I am not writing any of the answers. Students, please copy the questions and then answer. Mention any 2 properties of electric field lines. There are many properties, write any 2. It could be for 1 or 2 marks. Explain why no 2 electric field lines cross each other. Just now we discussed explanation of this. This is 1 or 2 marks. This is for 1 or 2 marks. Mention the relation between electric field and electric force on a point charge. F equal to Q into electric field. What is the direction of electric force on an electron in an electric field? What is the direction of force? What is the direction of electric force on an electron in an electric field? This is electric field. Electron experiences force opposite to the direction of electric field. So you can write opposite to the direction of electric field. 1 mark. Explain why magnitude of test charge should be very small. There is electric field due to a charge Q. If we keep test positive charge, then this positive charge will also have some influence in this region. And the influence of test charge should not alter the influence of this given charge. For that reason, magnitude of test charge should be as small as possible. Mention any 4 characteristics of electric field lines. 4 characteristics. It can be for 3 or 4 marks. Draw electric field lines for a point positive charge. Positive charge. These are standard questions, important questions. Make sure that the lines of force are directed radially outward. Make sure that the electric field lines are radially outward. Draw electric field lines for a point negative charge. Negative charge radially inward. Next, electric field lines for an electric dipole. Electric dipole means positive and negative charges separated by small distance. Equal and opposite charges separated by small distance. Plus and minus means the lines of forces are from positive to negative. Like this. Draw electric field lines for 2 equal positive charges separated by some distance. Yes, you know how to draw. Draw electric field lines for 2 equal negative charges separated by some distance. Derive an expression. 1 mark, 1 mark, 1 mark. Derive an expression for electric field at a point due to a point charge. It could be for 3 or 4. Even can be asked for 2 marks. 2, 3, 4.